tonight we're looking at 2910 software. So they released it back in June on their GitHub. I've gone ahead and already pulled it down and have it open in VS Code here. This is the first time we're doing a code exploration or a software exploration of a team. So I've never done this before. We're doing this live. We'll see how well this goes. I know a little bit about 2910 software from just reading some things on Chief, but I've never looked at any of their code directly yet. So I know they don't run Path Planner for their autos. They do some point-to-point stuff. I know some of their PID stuff's a little bit potentially simpler, where they're only doing like P on some of the motor controller things and not worrying about some other configuration on other constants and things. That's kind of all I know going in. And as we go through it, we'll find out together kind of how some of this stuff works. Okay, so jumping into their main repo, when you open it up, you open up the whole folder, we get their source directory, which is mostly where we're going to be looking through most people's code. You kind of come in and you see their robot folder and everything. There are a couple other things in here that give us a hint at what might be going on later on. So they have an Advantage Kit license and the FRC 254 license and the 6328 license. So some of those things means they may have borrowed some amount of software from any of those places. Maybe not, maybe been left in there. A lot of people's code bases aren't the most kept up to date all the time, but it is something to see. Similarly, we have some Vision IO Limelight tests. So we know they're doing some stuff with Limelight probably, or this probably wouldn't be in here. And then we also know kind of a little bit about what the robot looks like, because we did that on Thursday. We went over the robot and kind of saw how they were doing things there. Okay, so looking in robot directly real fast, and they also have robot containers, so we'll kind of play through both of those. Let's see, so we can see they are running some amount of Littleton Logger, which is a lot of Advantage Kit normally. Littleton Robotics is 6328 Mechanical Advantage. And so they have some of that stuff going on here. And then some normal WPI lib things, and then all of their 2910 robot code directly. And yeah, so this is extending logged robot. That is the base file for Advantage Kit. The logging and playback framework that 6328 wrote, and quite a few other teams have used as well. A lot of this is all that's set up for the logger. Some basic things here on whether changes have been committed and stuff, so you can actually log on the robot whether it's like an actual committed change or not. So you can, if you're looking at a robot log, you can see if somebody just like tested something without pushing out the commit, which is kind of nice. I'm not going to go through all of this. We're going to try to get into where they actually get their robot going at some point. They do have some current mode switching for real sim and for replay, all stuff you would use for Advantage Kit, kind of normal, nothing too crazy. They are setting up some amount of their shuffleboard directly in code. So they're doing like git tab and adding things directly to certain tabs programmatically, so they can kind of define where some things are located and everything. I don't think I'm worried about most of that. That's all normal stuff for the most part. Let's see. So most of robots just going to be their general things that make sure the robot's running through all the different modes. So robot periodic is the stuff that's going to be running every loop that the robot runs through its software. So it's its basic stuff. It's running the command scheduler to make sure it can actually run the commands, updating smart dashboard values, updating shuffleboard. And then if it's in simulation, it's silencing the joystick warnings, but that means they're leaving them on if it's actually running on the real robot. We disable them most of the time because we can figure out if the joystick's not connected, and we don't need it telling us every second, because it gets kind of obnoxious when you're just testing things with a single controller if you leave them on when you need both controllers, or when you instantiate both controllers. let's see, disabled init, not doing anything too crazy. It's resetting the auto chooser every time they go into disabled. And then they are throttling the vision system to 0. Look what that does later if it comes up again. Yeah, and they basically just say, yeah, if we're in disabled, we want to be in default state coming back. So if they are in the middle of scoring L4 or something, and the superstructure wants to be up at the L4 score state, and they get disabled, they basically tell it, hey, I want to be in my safe home state if I come back online, instead of trying to like repeat back to L4 and things move and jump around when people don't expect it necessarily on power backup or on re-enable or anything like that. Yeah, updating the auto chooser during disabled periodic. That's all they're doing there. Nothing too out of the ordinary. Teleop init vision system is still set to throttle 0. So and autonomous init. So they're always setting this value to 0 at disabled init, auton init, and teleop init. Yep, nothing else too out of the ordinary in robot. So a lot of teams will use robot container to actually build out their subsystems and things. We do it all in robot on 3847. We don't like having the extra file. It just kind of depends on how you structure your code. But this is where we can start seeing how they break up their subsystems. So we have swerve, vision, arm, intake, LED, climber, and they have an operator dashboard that may or may not be a subsystem. It's in their util class, so I'm not entirely sure. That may just be where they're generating it there. Let's see. And they have their superstructure, so that's used probably for their state machine, would be my guess. So that's kind of how they structure everything to be able to control each part of the robot together. They'll call the whole thing the superstructure, even though that's probably arm, intake, climber, kind of all together. Just making sure everything's in the right position together and never going to collide or hit or do anything out of the wrong order or anything like that. Yeah, it looks like they're only instantiating one controller, so they're probably only running a single controller, not having a pilot and operator. Get robot constant, so we can see they're getting some sort of robot identity. So we can go see how they're doing that. Is real, so they're pulling MAC address from the Rio. And so that gives them the ability to swap different things from 3 different robots. And if it's none of those, it pulls this other robot here. So they have 4 different robot types that exist for the real robot, and then simulation as well. So similar to what we do it off the Rio address that it has, or the serial number. They're just doing it off Mac. We used to do it off Mac. Both work. It's just some unique way to identify each robot. A lot of teams have different ways of doing it. And so that's how you're able to get your different module constants. So like the encoder offsets and things for each robot, all of those are going to be a little bit different if you have a comp and practice robot, or if you're running this on backup code or backup robots or anything like that, or older robots and you're just trying to run the same software. You need to have some way to switch the constants around to make sure it works. Let's see. Yeah, normal swerve initiation, initialization, intake, camera configs. Yeah, nothing too much out of the ordinary here. They're just kind of going through, initializing everything, pulling from constants what each port is configured as, and some like actual full ARM configurations. So you can like see what ARM constants are. They all seem to just return based on location. Interesting. Okay, yeah. So then they're coming back, and they all are in these different files for the configs for each robot. So for like the Loki robot, you can go through and you can see the different port configurations, Canivore, which one is, yeah, so which extension, shoulder, wrist, what each of those are. And those are all defined down further, so we have all those CAN devices being built up, so they have the full port map for each robot, where all the swerve motors are. We know like which CAN ID each of them is assigned to. Front left steer, front right steer. Well, that's getting confusing. Some of this may not be running, I'm guessing. Oh no, that's the encoder versus the steer motor. So they just redo. I got you. So yeah, so their encoders are 1, 2, 3, 4. So each device on the CAN bus can have. They can override use the same number as long as they're not the same device. So you're allowed to have a front right steer motor be CAN device 4 because that's a Kraken, and you're allowed to have the front left encoder be device 4 because that is a encoder, and so the system knows that you're not asking for one when you need the other. We try to avoid that. There's enough numbers that we can normally have individual numbers for everything, just so we know specifically what each thing is. If we see a CAN ID or anything, or if sometimes every once in a while the Phoenix tuner or something will come up and it won't have the right device. It'll just have like blank generic device and you'll have an ID for it or something. So we can get rid of those problems. They're pretty rare that any of that happens, but we've seen it every once in a while. And so we specifically don't do that, but it's totally fine too. And so yeah, so that's how they're going through and just doing basic config things. Nothing else too different in there. All your normal swerve configs are handled in here. A lot of the same constants and things, and then building out the module constant files to be able to initialize swerve. This is becoming pretty standard. This is kind of the standard way CTRE does it. We've written basically the same thing and wrappers to go around all of this as well, to make some of the configuration a little bit easier, and so that we're configuring based on a previous one and not having to like rewrite it every time, because otherwise we like wouldn't update stuff as well. All right. So in robot container, we can see they're basically going through and initializing everything. And then here they are just having the full configure bindings done in robot container. So this is where you're mapping all of your controller buttons to whatever actions they're going to do. So they can make some new triggers directly. Superstructure has home button been pressed. On true, instant command, tear all axis using button values, tear carriage. Yes, they're like setting everything to 0, and then they're going to have their LED pattern display that the robot arm is at 0. Pretty normal stuff all the way through. Yeah, on stick click, so this is left stick on true, toggle reef selection methods. They have some things happening on like their actual left stick button, which a lot of times gets mapped to like a back button on a controller or something. Most people don't like clicking the joystick, but sometimes you actually use it. Most of the time those get remapped to one of the extra buttons on the back of some of the programmable controllers. Yeah, a bunch of these other ones are just setting different states. So if we need to do specific things, you can. Your button. Yeah, so they have some amount of configure button binding command that they've kind of overhauled here to allow multiple commands to be pushed to a single button based on other states. So we'll get into how superstructure works later. But we can look at this method directly here. So has a straight coral condition, has a horizontal coral condition, has algae condition, and no piece condition. So there are basically 4 different options that this configure button bindings takes in. So based on whenever they hit left bumper, it's going to do one of 4 things. It's either going to score left L4, score L1 left top, move algae to net position, or intake algae from the ground. So any of those things can happen based on what the robot currently is holding in its hand or in its gripper, either coral in either of the 2 directions or algae or nothing. And so they do that a few other places. So like left trigger, they score left L3, score L1 left top. So those are actually the same there. So either bumper or trigger is going to score in the same place for L1. Except in this case, for algae, it's going to put it in the processor position. And in the other side, it's going to intake algae from reef. This is very probably directed to where it knows like where the reef position is supposed to be, where the algae is supposed to be on that clock face of the reef. It knows where the robot is, and so it can figure out, or which tag it's seeing at least, and then it can figure out which height to move it to and everything, so the pilots don't have to do any of that. Left bumper and right stick, so they have a modifier with the right stick here. That's, again, probably push to a back button or something, but it could be the actual stick. I'm guessing, 'cause I think that's just, yeah, that is just the button. So in that case, we're scoring L4, and then wait until we don't have a coral, so it's not has coral. And then we intake algae from reef. So this is basically they're able to very quickly do the score and then intake right afterwards on that button combination. The advantage of potentially only having one controller or just like a pilot without an operator is they don't have to sequence their commands at all, right? The one person thinking through what's the next button to hit is able to just do the buttons and do the commands and know what the robot's doing entirely and know what to expect because they're the only one controlling the robot. However, you do need a lot of very trusted automation on a single controller because you do only have so much. You only have so many buttons you can press, and there's only so many things a single person can do and remember and know how to hit to succeed in whatever they need to do. So there is a lot more, there's a little bit more cognitive load on a single person having to remember what each button is, but most of it is trainable. Teams have had a lot of success with a single pilot operator or a single driver. Teams have also had success with 2 where they're communicating and sharing the responsibility and kind of the cognitive load of getting the robot into all the positions or whatever it needs to do for its scoring task, shared amongst 2 people. Both can work. Sometimes it just depends on the game. Sometimes we'll design to where we plan for 2, but then we slowly move stuff to the pilot as more things get automated and make it easier. So like the 2024 robot had had an operator, but they had very little to do by the end. The pilot could do basically everything on the robot alone. Let's see. Yeah, so the rest of these are all just the rest of their button bindings, so we can go through and see how they do single control all the way through. Having those extra states there, knowing what game object it has, and trusting that and knowing that it all works allows that to be a lot easier because they can override all of those buttons based on what game object the robot knows it has. And that's kind of what it's doing all the way through all of this. Yeah, you can see they have some manual modes here, so they can go into like a manual L2 to be able to drive in and score it in L2 without having the automation happen, versus a score right L2, which is going to be a little bit different, where it's going to like automatically do the lineup. All right, so those are just our getter methods for some of the values that are in here. Yeah, so that's pretty much most of what's in robot container. So you still don't really see how a lot of the robot actually functions yet, but we kind of have the high level of what the controls are, what the different subsystems are. So we can see a pretty good idea of kind of what they're going for and how it works, but then we have to dive deeper to see exactly how they do a lot of those things. All right, so robot state. This is one of their custom ones. We have a states file as well. They're going to be a little bit different. Let's see what they're doing in this one. So, yeah, so this is a singleton. There's only one allowed, and it returns the instance of it. If you haven't done computer science, you'll learn the singleton pattern. We use it occasionally. We also know that it's our software, and we shouldn't ever call it twice, so you can kind of get away with not doing it in FRC sometimes. It is good. It's fine standard practice. It's not required all of the time. Let's see. Yeah, so this is a lot of their swerve things, so like chassis speeds and some amount of their vision observations. Other things like that are getting in here. Yeah, so how they're adding pose estimates or observations, I guess, and then generating the estimate somewhere else, I'm guessing. Yeah, so they have some simple methods. These are ones similar to things that we about, like get closest 60 degrees. So that's telling you, based on your rotation, what the nearest 60 degree to lock onto is. That helps with your the 6 sides of the reef. Yeah, trying to figure out which way you should be scoring, whether on the front or back of the robot. So they're getting closest rotation to face nearest reef face. So how to very quickly turn and get the right face to the reef so you can score either forward or backwards. Again, this specific call will run out of time if we try to go through each and every method, so I'm definitely not going to do that. But these are definitely useful to read through and see how they do, because you end up using methods like these in a lot of games if you need to figure out how to get the robot turned around in a specific direction, or maybe you need it to be the front or back or left or right if you can score on different sides of your robot, or figure out where you are versus them. A lot of those same methods kind of work. It just depends on the exact details of whatever that game is. Yeah, and we have get closest tag ID. So based on the poses, the definite positions of the robot, we're able to see which tag is closest. And so that helps in your vision system to know which one you're trying to look for and which one you're going to aim at to actually score on the reef. Okay. Let's go ahead, before we look at superstructure, we can look at how like a single one of their intakes works. So this is kind of standard setup for a Advantage kit. For any of the robot code using Advantage kit is you'll have these intake IO classes where they kind of establish how different parts of the different information that each of the subsystems will need. That could be all the way from like the voltages here, currents, velocities, all that, and it's all stuff that's going to be logged, and then it's all stuff that can be replayed back through the simulator, so you can like actually get data from the match And there's whole present and Mechanical Advantage and them do whole presentations on how this all works. I'm only going to do the very quick version of this. But you can get data from a real match, run it through your code and like replay what happened in the match, but then you can even change your software, replay that data again, and see what would have changed on the field. So if your like aiming wasn't quite right, you can replay the actual match, giving all the information, and feel like, oh, maybe I caught something that made it aim a little better, or maybe I caught something that made sure that it knew where the coral was. Like you can't change the outcome of the match clearly, but you can actually see your code working on real data that was collected from the field if you set all of this up. How often teams actually do it, I don't really know. Like some teams do it a lot, some teams set it all up and then never use it. So there's some amount of value deciding how important it is and how often you'll actually use it or not. In here it goes through kind of how to all get all of those, how to get all those values for the specific intake. So it's setting up, like you can see, top voltage, top supply current. Those are all the same things that are in here. So you have top voltage, top supply current. And so this is just showing how do you actually get all of those, what methods they actually have to call to produce all of those values. This also, in theory, allows you could like have a single intake that if you wanted to be able to swap different types of motors on, you could write an intake IO Rev or Neo or something, and you could do these same things as if you had a Neo and a Spark Max there, or a Neo Vortex or whatever it is. And you could kind of have the same things if you wanted to sub them in and out. In reality, you're probably not doing that on a robot, basically ever. Update inputs. Yeah, so all normal kind of Advantage kit style things. And then inside intake subsystem, they have their intake IO, all the normal things. Not sure what data processor is. What is that? Data refresh data. So this is just more of how they're doing some amount of their own data logging, separate from Advantage Kit, it looks like. Yeah, it seems like. Yeah, it would take me a little longer to figure out exactly what they're doing there. It's some part of the logging system. Oh, but that's how they're doing IO update inputs through that. So maybe it's to help synchronize that a little bit. Because that's running IO.update input. So that's running the that's running this code on that loop that gets done there. So I'm not entirely sure. Yeah, so it's running that loop on a different thread. So that may just be that they're multi-threading out all their IO things, is what it looks like is happening here, as far as I can tell. So potentially useful. You can get a little bit better time accuracy possibly doing it that way. Shouldn't change too much on how things work, but it's just kind of teams decide how much multi-threading they want to play with and deal with. That does work pretty well though with the IO since everything's getting updated that way. Yeah, that should be fine. It clearly is. They have had it working. So, okay. They have some enums to set up their states. Different wanted states versus the actual system state. So like you want to be eject algae, the system state is ejecting algae. And so those are named a little bit differently. These are all active verbs. These are more like the commands basically. So these are things you tell it to do. These are what it's actually in the middle of doing. Yeah, so they have more logging things, logging their system states and wanted states. And then all of this, basically the way state machines work is you're handling all the state transitions. So you have a switch statement on wanted state, you decide which of these things to go to. So if the wanted state comes in and says we want to eject algae, has algae entered false, yield system state to ejecting algae. So yeah, so it basically says needs to that work? Eject algae. So system state should go to that on its yield. Not entirely sure how some of this works. I'll have to look into it. Well, as we figure it out, we'll see how some of this works. Some of that may be how superstructure works. We'll have to look and see what they're doing in there. So system state is just the enum. And so, yeah, so some of that is basically telling it which system state to go to. And then, okay, so yeah, and here they have apply state. So then it's able to check some things beforehand, and then it's basically able to say, okay, now I'm ready to actually eject algae. And then it'll actually do it. And in this case, top motor voltage will go to the ejecting processor, or I guess ejecting algae, the ejecting top algae voltage. They'll swap that, they'll set up that motor to do it. And then they won't have, it doesn't look like they set the other ones at the same time, but those will get set based on default and things, and those will get set pretty quickly. But yeah, so all of these are where they actually set the motor voltages for their intake. It doesn't look like they're doing anything else but motor control or voltage control on the intake. So it doesn't look like they're running PID or anything. And they're just able to do it with voltage everywhere from what I can tell. And then we have a couple of their other mechanism to kind of check some of the states, so you can check whether it has a straight coral, horizontal coral, some specific things like is the bat can range. So those are the sensors on their intake that can tell some of those specific what's being blocked or not. So you can see is front can range trip, back can range, any of those to decide which coral they have. See if we can look in ARM. So ARM has a little bit more. So ARM has all three of extension, shoulder, and wrist. But then ARM subsystem is its own subsystem, but they have each of those IOs. So they have one big subsystem for quite a few motors because their extension and shoulder are both 3 motors each, and then the wrist motor as well. But they basically are saying we want to always be commanding all of these together at the same time, which makes sense for an ARM that integrated. Yeah, so similar things that we already saw. They have that wanted state and system state, and they also have a previous wanted state, so they can keep track of what they asked for before. Yeah, so same, they're starting that data processor again, having the update inputs on each of those 3 IO files, which again should be doing very similar things to the other one where they're just getting out your angles, supply currents, all of those things that we saw intake doing. So we're all pretty similar. They are processing inputs and recording outputs. So again, more for the logger to do. And then they are checking for the wanted arm pose, and then applying states in the periodic loop as well, and then keeping track of the previous wanted state by just saying this is what we currently wanted. So each loop, they're just knowing what the previous loop wanted state was. Yeah. Okay. Similarly, they have all the handle state transitions. This is definitely a lot more complicated for the arm than it was just for the intake for some things. So your case home basically checks if driver station is disabled, does something, or isn't disabled, and then goes through and makes sure, set some of the arm constants. Less than, okay, no, it's just checking if, let's see, so it's checking if the shoulder angular velocity is less than shoulder zero velocity. And if it is, what does it do is the question. If all of those cases are true, it eventually says it can do things like homing wrist. It should also be able to home the rest of it somewhere in there. Let's see, yeah, so homing shoulder and extension happens here. Homing wrist happens in a few different places, so it's waiting on some things for time. We can go through and figure out what all of that is, but I think we're running out of time at some point. It does check, is wrist homed? Is extension and shoulder home true? If that's true, it'll tear wrist, so it'll put it back to 0. And then it'll check our system state back to idling. Otherwise, it will run, let's see, it runs homing wrist, it runs homing shoulder and extension based on a couple different things. Yeah, so pretty much all of these are just doing the different home things. Otherwise, the case is either idle, and it's just going to set to idle, or the case is moved position, and it's going to tell it to move to position. So really, it has a lot of cases for home just to make sure everything's protected and homing correctly. Most of the other time, it just says go to the position we told you to, and it's going to be in that move to position state. Let's see. So yeah, so homing shoulder and extension. So all the different actual states it can do. A lot of these are, it is just setting duty cycle for some of these basic ones. So homing shoulder and extension are just setting duty cycle things. So it's not doing PID for any of that. They're just telling it to move at negative 0.07. So it's just asking it to go backward slowly for the homing situations. Same with shoulder, same with wrist. They are just going to be moving back relatively slowly to where we can zero everything and know exactly where it's supposed to be. And then idling, it just sets every duty cycle to 0. And then move to position is where it's going to do most of its work. Is extension and shoulder homed, and is wrist homed? Okay, if coming down from L4, if scoring over back, set target. Okay, so yeah, so it's setting target angles on some of the things like shoulder. It's scoring over back or over front. Extension length. Okay, yeah, so you have wanted arm pose here is getting your extension lengths, and so it's choosing when to set some of these values. So it's choosing when to set the extension. It's going to set some target shoulder things to make sure things are clear, I think. Set target angle, get shoulder angle, wanted arm is near. Let's see, if we are not close enough to where the shoulder is supposed to be, keep the extension at 0. Else set the extension to move. Yeah, and so these are where you set your wrist. That is where we set our shoulder, and that's where we set extension, basically. Yeah, and shoulder set angle. Okay. Yeah, so it's pretty much largely just telling them to set at the target angles, but there's some specific cases here that it clears through based on if the extension is far extended. So like if it is coming down from L4, it does some specific things for the shoulder for a little while until the extension is retracted, and then it's able to set the normal thing, so then it actually sets the shoulder where it wants to be, because what you don't want is for like the whole arm to flip all the way down first and then the extension to come in. That might run into another robot. It could break things. That's my guess of what's happening here. And then, yeah, and then same with wrist. It's able just to set those pretty quickly. Okay, so yeah, that's basically how the basics of the state machine for the ARM subsystem works. So relatively not too bad. If we look at the actual superstructure file, we get to where a lot of the software for this robot is, I imagine. So this is a, yeah, 1,700 lines of code. And it's going to detail a lot of what this does, right? We have all of the wanted states, all of the current super states, and so that's where you're building up a ton of what the robot can actually do, is in here, not necessarily in all the subsystem code. Yeah, so you have your wanted super state, and then based on each of those, you can tell it what its current one is, it looks like. Has some changes for what default is based on what it's doing. Yeah, most of these can just go straight in. Sometimes they check, or so here they have some checks for whether it's an autonomous or not, and so whether you're scoring auto L4 or teleop L4, just based on what it's in auto, which is kind of nice. So that's a pretty quick little way to be able to have two different things go on, but still stelling it just to score right, but then you just check if it's an autonomous or not. Let's see, yeah, all the rest are just kind of mapping itself. Some checks in here for like climber things. So yes, there's some checks here to basically allow for some very specific cases of like the arm going in and grabbing from the reef. It needs some like intermediate position and things for that. And so then it has to set that to true, and then later it will check that that's true, and then do something to have, after it's done the intermediate or intermediate pose, it'll then set this to true and this to false, and then whether it has drive actually reached there and everything too. So it can have those values already. They're also super easy to read because they're really long variables, but that allows them to be very easy to read, and we know what it's actually asking. Without ever having looked at this robot code, you can know exactly what this variable is going to be used for, and only that thing. Yep, and then through here, the current super state, based on what it does, it has the method that it wants it to do. Most of these are just going to be direct maps to that thing. Score L1 right top is scoring base false, constant super scoring side right. Um, okay, yeah. So they have based on where they score L1 and the auto align, they can choose whether they're doing like the lower level or the upper level, where they did the little log stacking 3-log thing on L1. And so they have a single method here for those that they can pass in a couple variables to swap that, so they didn't have to write a method for each one of these. It can be a little bit simpler. Same with some of the other teleops. Yeah, they're just basically able to pass left and right to it. So again, they can have a single score L2, score L3, and then just pass whether it's left or right. All of those are normal. And then here's where you actually have the methods that are actually performed when each of those states are happening. So during home, they're displaying a display robot 0 is on the LEDs, and they tell everything to go to home or home, and then idle once they finish. Yeah, we can see what happens when they're holding algae. The arm, we want it to move to the hold algae arm position. Swerve is going to be set to teleop drive because we want to just be driving around when we're holding algae. We don't want it to be like auto driving anywhere. Teleop velocity coefficient, regular teleop translation coefficient, so basically not telling it to go into like slow mode or anything. So you can very quickly in these like states tell it how fast you're moving, which is super nice. Same with rotation velocity. LED is now, yeah, as LED is saying to hold algae as well. Climber is just stowed because you don't need it to be doing anything else. And then intake, you basically say, have we reached the set point? We can hold algae. If not, we can hold algae harder. And so they have a couple different things they can do to spin the motor up, I'm guessing, for making sure they don't drop algae. Similar things happening with hold coral, telling it to go to different places, making sure the arm is ready. Same with all the swerve stuff. So they can set rotational velocity. So if the should hold straight is if you're straight or horizontal. If straight is true, it's 1.0. If horizontal is true, it drops down to 0.6. So I'm guessing that's because if they spin too fast while holding a horizontal one, they would just throw the coral. That would be my guess, is it's held in less tightly than the straight ones that are held by all 4 of those wheels on their robot. But there could be another reason why they want to spin slower during that time, but probably because they throw algae or throw coral. Yeah, and then climber stays stowed like you'd expect. So then most of these are all going to be pretty similar, able to define pretty much everything for each state. This is a pretty nice way to go about doing things. We'll probably copy some of the way they do some of this. Yeah, so we can see some things like how they intake coral from the ground. So they make sure if we're intaking coral from the ground, we're not ejecting coral, so that should be false. This is hold coral straight is true here. So there's 2 different ones. So there's intake coral from ground, then intake coral from ground horizontally. So if we're in autonomous while doing this, we're going to current extension position equals a certain amount. So they're saying it should be, if it's, and it's greater than 30, and the wrist is greater than 120, they're going to target arm pose, ground coral straight, clamped arm pose, get extension length, get shoulder rotation. So they're basically telling it they want it to go to the clamped arm pose, but I'm not sure why that's different here if we are in autonomous. So let's see. So target arm pose get extension length. Yeah, so that's just getting the current extension length. And the shoulder angle, they're getting the current shoulder angle. And they're rotating it. Oh no, sorry. So that's getting the target arm pose one. So those are the target arm pose from ground coral straight. So they're getting those, and then they're adding the rotation 2 degrees for the wrist. Yeah, so you're basically saying, okay, so if we are extended and we're the arm is in some position, we're going to go to our target arm pose, the ground coral straight arm positions. That's what these are. But they're clamped for some reason. I'm not sure why. I think that's just to move it down, because that should be your wrist position. Yeah, because their arm position here is extension, shoulder, and wrist. So that 125 is their wrist position. And they're just always basically telling it to go to there. Else if we're not in autonomous and the back can range is tripped. Oh, sorry. Once we're through this, so basically once the arm is lower and here, we now can check if the back can range is tripped. If we're in autonomous, we're going to move the arm to the moved position, hold coral auto. Else, so we're not in autonomous, we're going to do hold coral teleop. That happens if it's actually been tripped already. Else, we tell it to move to position with ground coral straight, so we're able to move it straight there. So this one had to happen for some reason to kind of leave the wrist in a specific position as they brought it down. And then once it's low enough, like once this is brought in and this is under 30 and the wrist and the shoulder's under position, it's able to just go to the normal position, which is basically the final part of this. The else is when we're intaking ground coral, we largely just want to be in our ground coral straight constants, and we can go see what difference theirs are. So yeah, so that's just the rotation is negative 0.2 when we're actually ground intaking. But here they're basically like keeping the wrist back for longer, and then they'll flip it out to actually do the intaking. If get current extension position is less than 10, intake, collect coral straight. And then it says display intake and coral. Okay. So yeah, so then once we're already there, so basically is back can range trip, so that's the second sensor. If the coral's already back there and it's triggering that sensor, they move into the hold coral mode. For horizontal, yeah, and they have whatever this is for the actual wanted state. So on the intake, we didn't check that real fast. So yeah, collect coral straight. And then somewhere in here, it tells us what that means. Collecting coral straight. And go see what they actually do with that. Nope. Yeah, collecting coral straight. So yeah, so it just has those different values. And for collecting horizontal, yeah, so they just run when they're collecting coral horizontal, they don't run the right and left motors at all. They just run the top one. And are able to grab coral pretty well that way. That's pretty cool. Okay, back to where we were on superstructure. Times it. All right, we're getting close to the hour. But yeah, we could basically go through and see all of the different ways these their superstructure states work. They're going to be pretty similar. They don't have to do some things, right? So their intake coral from ground has some more auto stuff because they actually have to do that in auto when they were doing the pre-setup coral, the spike mark ones, where you're doing the horizontal, they're only doing that in teleop, so they don't need the other autonomous stuff. Intake coral from station has a little bit more stuff going on because there is, again, they had to be able to do it in auto as well. Pretty similar. Intake algae from reef, intake algae from ground. So all of these are pretty easy to read and understand because they have everything written out very nicely. Oh. Yeah, from human player. Yeah, so they had a setup for being able to intake algae from the human player. So that's if they wanted to do like the algae co-op processor loop where you put one in the processor on your opponent's processor, feed it back to your robot, and put the same algae back through, trying to get the co-op bonus. And then here's where they have their actual auto align code. Some of their other, yeah, so score L1 auto align, eject L1 2, score L1 in teleop, so we can see a little bit more. I guess that's L1. Let's go to L2. Okay, so going into L2 is observation present. So basically saying drive to scoring pose, and like which side. So you can say left or right. If scoring direction equals front, they have a set to be able to set the arm to the correct position for that, for L2 coral front. And then intake settings, they have it to index coral to forward. If we're scoring on the back, they can index coral backwards, so they can move the coral a little bit based on their sensors to get it ready to score based on if it's forward or backwards. Is ready to eject in teleop. Coral eject flag equals true. You can go through and check what they actually are checking here. So they're basically saying, is drive at the right set point? Is swerve at the right rotation? That's the tolerance. So it's basically saying, is it within 2 degrees? And has the arm also reached its set point? If all of those things are true, it's able to score. We were in score L2 teleop, I think. Yeah. So that's how it's able to know when it's ready to actually score for them, so they can auto score. If coral eject flag, then they can basically, if that is set to true, they can then go through and actually do the score. So automation level equals auto release. If scoring direction front, eject coral backwards, else eject coral forward. And then if we don't have coral anymore, we can then say we want to go to default state. So basically saying we finished ejecting the coral, we can go to the default state. So yeah, so that's all pretty much how they go through all of their states and things. It's pretty straightforward. It's very verbose, so it's pretty easy to read. So these are all things that people can read how all of their command states are working for the most part. A couple other things we didn't get to yet, so we can kind of see some of what their vision stuff does really fast. Um, let's see if it makes more sense here. So yes, they have their limelight things that are basically looking through. Let's see. So they have Vision IO for each camera. They're able to update and have each camera doing things. Yeah, calculating robot pose from each of the cameras. Vision system. Where they set up each of their cameras, but I may just be missing it. Yeah, get first. Let's get second. Okay, so they're just pulling that. Yeah, so it's getting each of the robot state like tag observations, and then they're adding those vision estimates to their robot state, which I kind of looked at very briefly earlier, to make sure they know where their robot is so they can do all of their auto align. Not sure what those are. Oh, those are just digital inputs for neutral mode and brake mode, so they can like set the arm and things to coast with mechanical switches on the robot, I'm guessing. Because those are digital inputs, so those are plugged in directly to the RoboRio. I don't think there's definitely a lot more here. I'm just trying to think if there's anything else we need to go over tonight, because I'm definitely a little over time now. I don't think so. Oh, yes, we can look a little bit at their auto. So they have their auto file itself is just the enum with code words, it looks like. Uh, oh, here we go. So yeah, so now they're explained more. So you have your 3x far left, far right, 4x far left, far right, 4x left, right, 5x left, right, and then mark pickup test. Auto factories. So let's see. So you're getting map. Let's see. Is that all in? Yeah. So in here is where they're actually making the autos for the most part. So they have the commands.sequence, follow, then score. And so they made a bunch of these like helper methods that are down here. So they have drive to point along with wait until basically until it's distance from end to path to move arm up, and then wait for coral release. So yeah, so their follow then score is doing all of those. So we can see what their drive to point does. So yeah, all of this is built into this auto factory class, which is pretty large. Yeah, like 500 lines. Get swerve system, set desired pose for drive to point constants. So you're setting the point, your max velocity output for drive to point, and then max angular velocity as well. And then new wait command, wait until command is at drive to set point. So that definitely works for the most part. So we can go see, this probably gets us into their swerve. Yeah, so your set desired pose drive constants are here. And then your command robot controller. So that's just setting the desired things. Oh, and then it's setting your wanted state, right? So now your wanted state is drive to point with those max velocities. And then once your wanted state is drive to point, it's going to be running its state machine in here with its apply states. And so if your wanted state is drive to point, it's going to set that to drive to point. And then we can come down here and see what their drive to point class or their drive to point state actually does, and it's all of that. And so that's how they're able to actually do the drive to points without path plan or anything. They're pretty much just getting the exact point and driving in a straight line to it. From what this looks like. Yeah, so again, definitely a lot more to look through. But this is a pretty good start to digging through their code. All right, I think that's it for tonight.